So hello dear colleagues, hello dear all who are ready to watch our panel via Zoom and YouTube. As it is pre-planned by the program of the conference Systems Analysis in Eurasia, we begin our panel discussion Advancing the Frontiers of Systems Analysis and Mathematical Aspects of Systems Analysis. I am Professor Igor Sheremet, and I shall be the moderator of our panel. I am Deputy Director for Science of Russian Foundation for Basic Research and Vice Chair of the Committee for Systems Analysis of Russian Academy of Sciences, being the IIASA national member organization. Let me begin from introducing our panel speakers. Professor Fred Roberts is a distinguished professor of mathematics at Rutgers University, the USA, and Emeritus Director of DMAX, the Center for Discrete Mathematics and Theoretical Computer Science, which have directed for 16 years. Also, he is currently Director of the Command Control and Interoperability Center for Advanced Data Analysis, the University Center of Excellence of the U.S. Department of Homeland Security. He is author of more than 200 scientific articles and editor of some 30 books, The Mathematics of Planet Earth, published at 2019 among them. His works has been translated into Russian and Chinese and deal with such varied topics as discrete mathematics, decision-making, sustainability, global environmental change, mathematical psychology, epidemiology, disasters, and pandemics. He is fellow of the American Mathematical Society. He received the U.S. National Science Foundation Award of the Association of Computer Machinery, ACM, and was awarded the title Doctor Honoris Causa by the University of Paris-Dauphine. Fred is a good friend of mine. We are co-chairs of the CoData Task Group, Advanced Mathematical Tools for Data-Driven Applied Systems Analysis, and also co-editors of the book Resilience in the Digital Age, published some 2 months ago by Springer in the well-known Lecture Notes in Computer Science series. Professor Abraham Neyman is Professor of Mathematics at Hebrew University of Jerusalem, Israel. He is one of the world-famous scholars in the area of game theory. He has served as the game theory editor for the journal Mathematics of Operations Research, on the editorial board for Games and Economic Behavior, and the International Journal of Game Theory. He served also as the president of the Israeli chapter of the Game Theory Society. Professor Neyman also held positions and have been a visiting scholar at such world-leading institutions as Stanford University, Harvard Business School, Cornell University, the University of California at Berkeley, Stony Brook University of New York, and the Ohio State University. In 2020, he became an elected member of the Academia Europaea, the European Academy of Sciences. Professor Ahti Salo is Professor of Systems Analysis at Aalto University, Finland. He has worked in the area of decision analytic methods and the application to resource allocation, efficiency analysis, innovation and risk management, foresight and forecasting. He is author of over 180 scientific papers and have received several awards for his research from the Institute for Operations Research and the Management Sciences Informs. Professor Salo has been the president of the Finnish Operations Research Society for 2 biennial terms. He has been visiting professor at the London Business School, the University of Vienna, and the University Paris-Dauphine. He is a member of the Government Foresight Group appointed by the Prime Minister of Finland, and also he was a member of the science panel appointed by the Prime Minister's office for obtaining scientific support for the management of the COVID-19 pandemic. Dr. Elena Rovenskaya is the Program Director of the Advanced Systems Analysis Program and also Acting Program Director of the Evolution and Ecology Program at IIASA. She is also a research scholar at the Optimal Control Department at the Lomonosov Moscow State University. Her scientific interests are in the areas of optimization, decision support sciences, and mathematical modeling of complex socio-environmental systems. Dr. Rovenskaya is leading a team of some 40 high-skilled scientists at IIASA who focus on the latest development in applied mathematics and modeling towards advancing systems analysis methodologies and applications. So, as you may see, we have the very distinguished and high-level experts at our panel, and now we may move to its main topic, which is, advancing the frontiers of systems analysis and mathematical aspects of systems analysis. Before I shall give a word to the first speaker, let me make a few remarks concerning the main content and objectives of our panel. Let me say that systems analysis is understood so far as a most general and widely applied methodology of consideration and solution of multiple complicated problems. Assessment of systems resource consumption, vulnerability, and resilience to destructive impacts. Systems optimization and design given external and internal constraints and objectives. Systems reverse engineering given the multiple measurements and signatures available as big data sets. Strategic and situational planning and scheduling the behavior in the highly volatile and often hostile environments. The cooperation and conflicts, and so on. This methodology regards large-scale technological, economical, social, ecological, biological, socio-technological, and any other kinds of systems. This methodology far and wide presumes consideration of systems of any nature from some general points of view and application of some basic mathematical tools, toolkits, and frameworks, providing adequate and constructive system description and handling their mathematical images. And this quality, systems analysis is often named science of sciences, referring to its integrating, joining role in systems formal representation and modeling. And namely, in this quality, systems analysis and high-skilled system analysts and scholars have the greatest value for decision makers from various national, transnational, and corporate policy and economy staffs. So let us make an attempt to consider the main issues associated with modern systems analysis, beginning from its mathematical background, then application of available mathematical tools to multiple problems, up to transfer results of this application to high-level decision makers and providing the right advertising. And by this we shall try to understand how the aforementioned mathematical background of modern systems analysis would advance its frontiers and make its application more and more useful. Keeping in mind these introductory remarks, let us move to our discussion. So with great pleasure, I give a word to Professor Fred Roberts.
Good morning, everybody. Can everybody see my screen?
Yes, we see.
Very good. So first of all, thank you, my friend Igor, for including me. It's an honor to be here and a pleasure, and it's been an honor and a pleasure to collaborate with you. I hope that will continue for a long time. So let me go back. Let's see, my slides are not moving at the moment. Okay, there we go. So I'm going to talk about the tools of systems analysis and new mathematically based tools that are related to decision support applications. And what I'd like to do is stress some of the applications and challenges that we face in systems analysis, and mention the types of new mathematically based tools that are relevant to those challenges. So, and my slides are having trouble moving along here. I'm not sure why. There we go. Okay, so we have remarkable new mathematically based tools, and those tools are really relevant to the problems of the planet that we all face, in particular the problems that have been highlighted in this past very difficult year. A lot of the work is underscored by the dramatic amount of data that's available and the amazing tools that can be used to use those data to make better decisions and influence policy. And that's what I'd like to talk about. So for some reason, my slides, there we go, are not moving very well. Okay, so the first theme I'd like to touch upon has to do with fusing lots of data to make better decisions. And here let me first mention some applications of modeling and simulation. Now, those are not new tools, but they have new ways of applying them. So I want to emphasize some of the urban issues that modeling and simulation might be relevant to. So as we know, the world's population is moving toward living in big mega cities. At the same time, climate change is having a serious impact on urban areas with more severe hurricanes and droughts and storms and heat waves and so on. About a decade ago, we had a superstorm that we called Sandy in New York City. And that storm flooded the subway tunnels. Already at that time, mathematical models developed by a professor at Columbia University were able to predict which of those tunnels would be flooded, and they were very accurate. And now the question becomes, and this is something that the New York City Climate Change Initiative is concerned with, is as we plan ahead for sea level rise in urban areas, can you predict using models and simulation which power plants might have to be moved because they're on low-lying areas, and which train tracks might have to be raised because they might be flooded and so on? So those are some of the new challenges that we face with modeling and simulation. Now, for a second application, I'd like to talk about the health of ecosystems and the concept of biodiversity. With biodiversity, we want to be able to measure how well we're doing in terms of the variability of the plants and animals and our ecosystems in general. And in recent years, tools like artificial intelligence and machine learning have come to be very helpful in measuring biodiversity, and in particular, helping to identify species. So we have, as an example, a project that's called Snapshot Serengeti. With this project, as well as many others, there are camera traps set up around the world in remote areas mostly. There are motion sensor cameras. They collect millions of images of individual animals. And there is now an app that has been launched by Snapshot Serengeti that uses deep convolutional neural networks and is able to identify whether what you saw was a lion or a leopard or a jaguar or whatever, enabling us to do that extremely accuracy, almost 94% accuracy. And that is an aid to identifying the size and health of populations. Now, the next step, which is the harder step, is to identify an individual animal, because you might have counted that lion multiple times and you actually would like to know whether it's the same lion you saw or a different one. That is the next challenge for artificial intelligence and biodiversity. So let me mention next a supply chain challenge as another challenge that has to do with getting lots of information and fusing it. So the recent blockage of the Suez Canal by a grounded container ship has had an amazing and widespread effect on the world supply chain. The supply of oil, the price of oil, the availability of food, the availability of microchips to make cars, which have caused some car makers to shut down. Empty containers being stuck at some ports and not enough containers at others. Here, we're beginning to see multi-agent simulation as being helpful to model supply chain operations, and in particular, to help predict the impacts of this kind of disruption. And in fact, the complex disruptions that we're likely to continue to see to the world's transportation system. And at the same time, such simulations are useful by making use of multiple intelligent autonomous agents to help us understand what kind of mitigation strategies might impact the disruption and reduce its impact. So another comment about climate change and vessel traffic has to do with the Arctic and the increased use of the Arctic Passage for vessels. And by the way, considerable possibility when there are choke points such as the Suez Canal would be Arctic passageways. Coming along with this are threats and challenges of oil spills. And we need to plan ahead for the possibility of oil spills in the Arctic. It's not the same as in many other parts of the world, because here we have long transit times, lack of infrastructure, remote locations, few roads, difficulty with the weather, and so on. Lots and lots of data exists about kinds of equipment that's relevant, transportation routes, communication methods, and so on. How do you decide how to allocate resources in planning for an oil spill response under uncertainty and at the same time having constraints in your budget? So what oil spill response equipment should be forward located in advance? What should be prepared to surge forward if there is an issue? How does the season affect things? What happens in the near term versus the long term? For all those questions, we're seeing the beginning of tools of stochastic programming being used to answer questions of those sort. So let me turn to the next general theme, which is sequential diagnosis. And here we have a variety of tests available. You choose the next test on the basis of results of earlier ones. Typically in medicine, for instance, you find that some of your blood result numbers are not so good, so you have scheduled for another test based on that, and so on. Here, tools like optimization and decision trees have turning out to be helpful. One method I would mention has to do, it actually arose with inspection processes for containers at ports of entry. But similar applications arise in education testing and testing for disease and so on. Here the problem is that the number of possibilities, the number of possible orders in which to do tests is just very large. And we like to represent the problem as a problem involving binary decision trees. And the question is how to find the optimal binary decision tree in some sense. And these decision trees explode in number. So even if you have 5 possible tests and you can do them in different orders, you can have over 260 million possible decision trees, binary decision trees, and you need better search algorithms to move from one binary decision tree to a better one. Sequential diagnosis is also coming to be used in testing for COVID. Here are large-scale linear programming tools like sensor tree are useful, and we try to optimally select from the available tests the best one according to price, availability, efficiency, and accuracy, depending on the roles of the person you want to test. Do they have to go to work right away? What kind of work environment do they work in, et cetera, et cetera. So let me turn next to the general principle of data-driven decision science. So what's new about decision science that hasn't existed for many years? The difference is data science and the availability of being able to, of a vast array of alternative solutions that we can compare. And here we have the tools of algorithmic decision theory, very relevant. And with algorithmic decision theory, we exploit algorithmic methods to improve the performance of decision makers. So I mentioned, for example, the Ebola outbreak in West Africa of 7 years ago. It should have reminded us that we were ill prepared for a worldwide disease epidemic. But unfortunately, I don't think we were all that well prepared when COVID hit. I will say that the successful fight to contain the Ebola outbreak was heavily influenced by algorithmic decision theory, which allowed us to accurately predict disease spread and how to contain the disease, and allowed the decision makers to understand things like how many beds and lab tests they would need and where and when to deploy them. And I think during COVID, the worldwide collaboration of modeling and simulation, making use of its literally tsunami of shared data, have helped decision makers save lives. So I'm still having trouble with my screen. Here we go. So let me turn next to another point of decision science. And that has to do with supply chains. So artificial intelligence and machine learning have enabled us to minimize inventories because we have extremely accurate knowledge of demand for goods or components. And that allowed us to get just-in-time delivery of goods. Very efficient until something goes wrong like COVID. And then we have shortages because we didn't plan ahead for surplus and stockpiles. And here are tools of algorithmic decision theory I think are relevant as we go forward and rethink the role of AI and machine learning in supply chain. So here we have modified tools of machine learning probably will help us identify alternative sources and changing priorities in a fast way. Maybe data-driven decision-making will help us support decisions about how large stockpiles should be, where they should be located in case of a natural disaster of one sort or another. So last theme, and I'll end very quickly, is information sharing. That is enable us, hopefully, for all kinds of organizations and individuals to work together while protecting their private information. Could be useful in applications where we have multinational partnerships to work on sustainable development, where we share information about energy use in the private sector, maintaining the private information that individuals or organizations or countries have while allowing them to collaborate. And here I just mentioned two tools that are under development. One is called secure multi-party computation, which allows multiple parties to compute something jointly, and blockchain that provides a decentralized record-keeping system that allows them to transact safely without requiring a middleman. Next tool I want to mention has to do with a Trustmark. That's a digitally signed assertion that shared between parties that allow you to trust someone. And that's important in disaster situations where we have lots of data as to damage and physical needs and so on. What can you trust about the data and the person who's giving it to you? And sharing information about water quality, air quality, flood risk, and so on. And the final thing I'd like to mention has to do with information sharing and identity and access management. Proving who you are and what kind of skills you have is critical in disaster situations and in others. So do you have the authority to do something? Can you prove you've been vaccinated so you can board a flight? Can you prove you have emergency medical training so if you show up at an earthquake or a hurricane, you can help? Can you prove that you're allowed to be in a remote wilderness area to study endangered species? This is a big area of research where generally called identity and access management, tools being developed to enable you to prove on your smartphone with encrypted information about your credentials to speed approval to get you access. It's also an important growing field of systems analysis, along with the many others I've talked about. So thank you for your attention, and I turn it back to Igor.
Thanks a lot, Fred. As we just have known from this brilliant talk, a mathematical background of systems analysis is not striving to some one unified mathematical toolkit. Rather, it is a wide set of various tools inherited mainly from the operations research area, which in fact may be considered the predecessor of systems analysis, with its objective to optimize behavior of large-scale systems. In turn, one of the most powerful and valuable areas of the operations research is the games theory, and there is a lot of interest regarding application of this theory to problems which are so far associated with systems analysis. So I think it would be of great interest for all of us the talk of Professor Abraham Neyman, being one of the world's leading experts in this area. Please, Abraham.
Without the slide, so we don't waste too much time. And I would like to start with saying that game theory has remarkably many tools, both applied tools and theoretical tools that are being used. And I was decided, since we are speaking here of system analysis, to pick a topic that is calling for research and incorporation of some of these game theory tools. And this issue is the transformation to autonomous transportation, autonomous cars, etc. So right now we all know that there is a lot of global effort to develop autonomous cars. And the question we should ask ourselves is, how would the world transitions from the current situation where most cars are being driven by human beings to the stage in which most cars will be driven by autonomous cars? And where is game theory entering here? Because if it's an autonomous cars, you could decide how it behaves. If it's individual driven car, it is obviously its decisions will be made by the individual optimizing his own benefits. And if all the cars would have been autonomous cars in the streets, then it is very easy to increase drastically the roadway capacity, because the distance between cars, because they will communicate between themselves with the 5G and each one will get and send signals from one to the other, they could reduce the distance, and the start of movement of all the cars at the traffic light could be essentially simultaneous. The question is, what should we do in the transitions when we are moving, and let's say at some point we are 50% autonomous cars and 50% individually driven cars? How should we handle it? Do we have any tools to try to design the system in such a way that the welfare will be maximized? The time of driving on the road will be minimized, the capacity will increase, etc. So if you hear me, can you state one type of difficulty? What will happen in a traffic light in which you have both human-driven cars and autonomous cars? What will be the difficulty there? I see my slide is not coming up yet, but can you hear me?
Yes, you can hear you.
You can hear me. Okay, so if all cars at the traffic light are autonomous cars, then they all can move instantaneously. When you have the green light, they could all move, and basically even you don't have to have a traffic light. They could all move in all directions, and there would be a central control that will tell each one at what speed and at what and where he could turn and where he cannot. But if you have some of the cars are being driven by human beings, it will be impossible. So the question is how to design. What is the model? What is a game theoretic model that can try to and analyze and being applicable to this situation. And this is the model of a stochastic game, but it still has several shortcomings that will be needed to overcome in order to apply it to this type of situation. In a stochastic game, you have a state variable. What is a state variable in terms of the movement of the cars in the system? It is basically a description of the positions of all the cars on the road and the direction where they want to get from point A to point B. It's a very huge data. Making optimization with such a huge amount of data, both of the individual side and of the autonomous car, which is somehow easier because it will be controlled by a central computer or by a system of computers, then you have to make, each one will have to make the decisions. So the decisions that the individual will make will generate a transition of this state variable. And each one will take the decision that will take into account its short-term benefit as well as the new position of the entire system. But the entire system will be a system that will describe both information that is relevant for his own decision, as well as information that is relevant for the total welfare of all the traffic that is moving from one point to the other. And therefore, on top, so this type of a model is called the stochastic game. But doing all this optimization, you have to be able to do this optimization with a limited amount of memory and computational resources. Some limits apply to the individual drivers and some much larger limits to the autonomous cars, because they will be equipped with very powerful computers and also will have system aided from the central computers for information and for the decision. So you need to study stochastic games not only with an unlimited computational and optimization resources, but with limited ones, and that you have to be able how to handle. And finally, as was mentioned, now the amount of data will be extremely huge. So you have to incorporate all these type of studies and to enlarge the study and the domain of stochastic game into cases by which the state variable of a stochastic game is a very huge state space, including many parameters. Some of the parameters will be parameters that are relevant for the individual optimization. Some of the parameters will be relevant for the general, for the central system that will control how the autonomous cars are driving, with the full objective of increasing as much as possible the road capacity, obviously minimizing the number of accidents, etc. Any questions? So
Thank you. Thank you.
Maybe just to summarize, the issue is the transformation to autonomous car drivers. The tools in game theory are stochastic games. One of the tools, there are additional tools, but for some of the aspects that I described is stochastic games, where the optimization is being performed with limited resources and when the data is extremely huge.
Thank you, Abraham. Let me make some short comment. Everybody who made an attempt to model critical infrastructures know that the transportation infrastructure is the most complicated and hard case. Energy infrastructure, healthcare, information, they're static. But if we want to model and simulate the transportation infrastructure, there is much more complex and computational complexity and dimensionality and so on. So thank you for a very interesting talk, which of course is of great use for all who deal with modeling of transportation infrastructure. Thank you, Abraham, once more. So now we have a much broader view on mathematical background of modern systems analysis and its applications. Some new opportunities in this area arise from the attempts to apply to modern systems analysis problems some are relatively fresh and novel tools such as agent-based modeling. And there is a very positive experience of IIASA scholars led by Dr. Rovenskaya, who have developed several valuable models for solution of non-trivial and complex practical problems. Please, Elena.
Thank you. I start to share my slides. Can you see them now?
Yes, we see.
Great.
All is fine.
Thank you. Thank you very much. Yeah, it's a big pleasure and honor indeed to present a little bit of our work in this very short presentation. And my talk actually resonates very well with the first talk by Professor Fred Roberts, who highlighted all these different alternative and complementary methodologies that are being used in systems analysis. And I just really, without coordinating, actually prior coordination with Fred, actually I would really continue on that and give in this talk a little bit of a general introduction, but then also 3 examples of specific research projects that we had at IIASA that really demonstrate the power of those methods. Before I do this, let me show you this slide, and many of you know this framework of VUCA, where these 4 letters, VUCA, stand for volatility, uncertainty, complexity, and ambiguity. And arguably, these are 4 major challenges to the decision-making of our current times. Yeah, when we think about public policy planning or challenges being faced by different decision makers at different levels, very often they are facing these 4 fundamental challenges. Yeah, volatility, I think we all understand, and now with COVID-19, we don't need to be convinced even more that volatility is really affecting us very, very strongly. Uncertainty, here we also mean both ontological and epistemological uncertainty that decision makers are facing. Complexity, of course, is ever increasing, and especially in the last decades, the global complexity of economic processes, of social interconnections, has really increased very significantly. And then ambiguity here refers to multiple stakeholders that are typically involved in any complex process. And not only every stakeholder has different interests, multiple interests, but also they are not always fully aware of their own interests and their own preferences. And even more so when they are aware, or to the extent they are aware about their interests and preferences, they are actually not willing to, in most cases, they are not willing to reveal those preferences. So all of that creates really big challenges for researchers who would like to support decision makers with systems analytical methods, tools, and insights. And that is what we are trying to do with IIASA, at IIASA. We come with this realization that once we are using actually models as a major tool of systems analysis, and by models, I really refer to a very broad concept. A model is actually any simplification of reality that helps us make decisions. It doesn't have to be necessarily a mathematical model, but of course, in the IIASA's research, we mainly deal with mathematical models that are expressed in mathematical language, but it can also be any simplification of reality. When we want to use models to support decisions and decision makers, those models have to be agile. Of course, they have to be reliable and relevant, but this agility element has really, so the importance of having model in this kind of agile manner that you can mobilize in in a way that is most useful to the challenges that decision makers are facing in that particular moment is really becoming more and more important. And those models really have to be able to deal with those 4 challenges. And what we are observing is that, of course, a lot of advances have been made in the course of the decades since modeling started to be used to support decisions. A lot of advances have been made, of course, to make those models really serving the purpose of being able to deal with volatility, uncertainty, complexity, and ambiguity. And Fred in the first talk alluded to some of the examples of those successes, but still, it's really important to realize that very often, in many cases, we are using the mathematical approaches that have been designed for a different purpose. They mainly were designed to meet the challenges and needs of physics or mechanics, which are very different from those challenges that we are now talking about. And therefore, even though, as I said, so of course, a lot of advances have been made and methods are becoming more and more suitable to deal with those challenges, still there is a gap, and this gap really we have to work on that, and that's the ambition of the group that I'm leading at IIASA, to make methods really be suitable to deal with these 4 challenges. And so here I also want to show this slide and remind ourselves that when we use models, it's very important to remember for what purpose we actually want to use the model, and really use models for the right purpose. Yeah, so this, for example, gives a list of different purposes, and in this case it's 16 plus 1 from this quite famous paper of Joshua Epstein, who is the founding father of social simulations, artificial societies, agent-based modeling, and this field. So he reminds us that there are all these different, really different purposes of modeling, and prediction, and he really puts it as 0. So it's of course the most obvious one, but it's not the only one, and may not even be the most important one for some specific challenges and situations. So we will not go through the whole list, but some of those purposes I like in particular. For example, models are really important to explain new phenomena that we now see actually with COVID-19, the proliferation of these modeling exercises that are using this relatively simple compartmental models, such as SEER model and all the extensions, in order to explain the dynamics, yeah, not to predict, but explain. So, but models can go further, so they can do all sorts of useful things, such as, for instance, discover new questions. They can illuminate core uncertainties or demonstrate trade-offs and suggest ways how to harness efficiency. And finally, more into the kind of social sphere, models can be used to discipline the policy dialogue. Yeah, so it's really important when we develop models and when we use models to use them with the idea in mind for what purpose, or when we develop it for what purpose it's actually being developed and how it will be applied. So after this general introduction, here I come to these 3 examples through which I will go very quickly. One example has to do with agent-based modeling. And it suggests ways to deal with this volatility challenge and complexity challenge. The second example will have to do with another method that is called stock flow consistent models that also helps us deal with dynamical systems and systems that exist out of equilibrium. And then the third example will have to do with dealing with uncertainty primarily through stochastic programming, or what we called risk-adjusted optimization and robust solutions. So in the first example, I want to show very quickly an agent-based model of people's behavior. In this case, we talk about pro-environmental behavior, and how to, so the question is how to stimulate, how to provide incentives for people to switch to more pro-environmental behavior. And what has been done in this work is that an agent-based model was built that represents dynamic interactions between agents, which are people in this case, and the environment, and also agents with each other. And what is important is that agent-based modeling allows us to model decentralized decisions. And that brings these models much closer to reality than other types of models. And therefore, this kind of way of modeling often helps to increase trust in models and therefore increase the uptake of the results that these models provide. So in this particular case, what is being done is that people's behavior with respect to certain pro-environmental or anti-environmental actions is being modeled, and this behavior is assumed to emerge as a function of so-called affordances. So these are the means that allow people to actually exercise pro-environmental behavior, but also social learning and excuse me, it goes in the wrong direction, and habits. And so here, for example, we can see one result that such models produce. In this particular case, it's in a stylized model setting. This means that this model is not, in this case, is not calibrated to any specific data or to any specific case study, but it considers this phenomenon as a general phenomenon of this pro-environmental behavior. So what we observe is that if we increase, so on the x-axis is if we increase the proportion or the amount of pro-environmental affordances, which means the means to exercise pro-environmental behavior, we actually see that the proportion of people who do exercise this pro-environmental behavior is increasing, of course, but it's increasing in a highly nonlinear manner. So what we can see is that when the affordances are relatively low, so in this area, so the people who choose to behave in a pro-environmental manner is increasing, but is only increasing slightly. But then we come to this area where this increase is very sharp, is very steep. Yeah, so there is some critical area or some critical range of the values of these pro-environmental affordances, in which this dynamics really becomes is developing very rapidly. And then we quickly get to that new level where further increases of affordances, of course, further increases the behavior, but already not so much as it did in this area. Yeah? So this highly nonlinear sigmoid function that we are observing here is a very important insight for those who want to plan those affordances. It means that it's really important to know where in this region, in this area, the current situation is, because if it's somewhere here, this means that one really has to invest a lot to achieve a significant behavioral change. But if we are already close to this transition period, it may be that one only needs to invest really a little bit to get a very significant effect. Yeah, so this kind of non-linearities is very important, and they are very typical for agent-based models, where the very simple behavior at the micro level actually emerges to the macro level and creates this kind of non-linearities. So this model that I'm talking about here was not only applied in this kind of stylized setting to come up with qualitative results and insights, but it was also applied to a specific case study. In this case, this is bike passes in Copenhagen. Maybe now it will be a little bit clearer what is implied by this kind of affordances. In this case, affordances are the bike passes. Actually, it's a length or the capacity of the bike passes, and that's so you can see similar shapes of plots here. So the model was able to reproduce the past dynamics of how citizens of Copenhagen actually started to use much more bikes rather than cars when the affordances, which is the bike passes capacity, actually increased through the investment of the city. So that shows us that this kind of nonlinear effects really do happen in reality, and therefore again, so this kind of models can really be helpful to support decisions where we really need to represent this kind of decentralized behavior of many different agents. I move on to the second example, and here I want to show stock flow consistent models of economic incentives. And as I said, so this aims to help us understand and provide recommendations on how to manage complex systems, such as our current economies. In this case, the stock flow consisted models based on data from balance sheets and transaction flow matrices, and they allow to simulate out of equilibrium dynamics of the economy. And what is important is that these models really strike a balance between complexity and kind of traceability of the models. So they are sometimes referred to as medium complexity models. So they on the one hand, they do represent a necessary level of details. At the same time, they are still traceable, and one can still oversee the model and also understand which phenomenon happens because of which specific details or interactions in the model. So in this particular case, we look at the following question. So everybody knows that this discussion around carbon tax has a lot of complexities, has a lot of feedback loops that it implies. So the question is how the carbon tax can help us overcome the climate change problem, and that how it can support transition to renewables. And here, an important phenomenon, an important feedback loop is taken into account, and that is the so-called sentiment. So what this model shows is that banks' anticipation through stronger climate sentiment. So if they take the sentiments into considerations, that the climate-aligned policy can actually smoothen the risk of financial stability and foster green investments. So these feedback loops that exist between the climate sentiments and the bank decisions, as we can see on this plot, can actually help us sort of show the efficiency of the in this case of the carbon tax policy. And now I move to the third example and come to dealing with uncertainty. As again was already discussed earlier in this session, uncertainty is really everywhere, and decisions that ignore uncertainty most likely will not be the best decisions that we would like to take. There are different types of uncertainties, of course, and then there are different ways, therefore, how to deal with uncertainty. In this case, we are dealing with, one can say, a relatively simple case, and this is when we can describe uncertainty by probabilistic distribution. Obviously, this is not always the case, and there can be, and there are a lot of examples where we have deep uncertainty, as it's sometimes called, when this cannot be done. But if we have the situation that we can associate distribution, a probabilistic distribution, with the uncertainty, then one can use what is called stochastic programming in order to improve our decisions through this risk-adjusted optimization. So sometimes it's one way of doing this is using so-called chance constraints, when we require that those constraints that we care about should actually hold with a certain probability. Yeah, so we allow that constraints actually may be violated, but this probability of their violation should not be too high. And usually that gives a more realistic kind of, or models that apply this approach provide a more realistic advice and policy options, rather than deterministic models that just say the probability, the constraints really must hold true. Very often this kind of solutions that come out of such approach are too costly, and the relaxing of this constraint can really be helpful. So in this case, I want to show very quickly an example of a system that integrates food, water, and energy sectors, and therefore called food, water, energy nexus model. There is no time to go into details. And what this model does is that it can show us how, depending on how much we are ready to relax this constraint, how much our optimal solution can actually change. In this particular case, we look at one province in China that produces a lot of coal, and the coal production requires water, and at the same time this province is actually quite scarce in terms of water resources, and there are also competing sectors for water, such as agriculture. So the question is, how should they how should they manage their very limited and very volatile water resources that are available in order to support these both sectors. And the goal of the decisions that the leadership of this province should make is to meet certain self-sufficiency requirements, so certain food and energy security targets. Yeah, this means that with a certain probability, they would like that a certain amount of food and a certain amount of energy is produced domestically. And so depending on this probability, and the probability then translates into policy options such as taxing and subsidies. Actually, we can show that, so for example, here in the round brackets, the percentages are these probabilities, so these self-sufficiency levels. So they can see how much of that self-sufficiency we can achieve depending on these fiscal instruments, which are summarized here as penalty cost term, but actually in reality they translate into taxes and subsidies. So how much of the self-sufficiency can be achieved depending on these fiscal instruments that can be applied. With that, I come to the last slide where I have a few general remarks summarizing what I just said. Agent-based models can be a suitable tool for modeling behavior and emergent phenomena. Actually, it's quite costly and the validation is challenging. Everybody who is doing agent-based modeling knows this very well, but nevertheless, it's a very powerful tool to represent behaviors and especially bounded rationality. Intermediate complexity models, such as stock flow consistent models, can be instrumental to explore a new phenomenon. So we saw the example of the carbon tax for illustration here. Risk-adjusted optimization enables the derivation of solution options that are not so sensitive to input uncertainties, in case we can represent uncertainties via probabilistic distributions. And what follows from that is, of course, as also was said by the chair of this session several times, we cannot have one approach, but a suite of different models of different complexity and type should be used to provide robust policy advice. So it's really the picture that comes from different elements that we as humans put together. So for maybe this will be in future replaced by artificial intelligence, but so far this is we as decision makers or experts, researchers actually synthesize and integrate, but these different pieces of advice come from different models of different type. Thank you very much, and I would be happy to receive questions or comments.
Thank you, Elena. Thank you for presenting the high level of IIASA work in the area of systems analysis, in the area of modeling global processes and global activities. So we have watched three extremely interesting talks on application of classic as well as new generation mathematical tools, comprehensive for description and solution of a wide area of problems of modern systems analysis. Let me affirm, however, that development of an adequate model and following its computations are necessary but not sufficient step in any problem solution. The success of all activities of systems analysts and scholars is dependent finally on how an interaction between them and decision makers from policy and economy staffs is organized, including assistance and advertising from the scholarship side. Professor Salo has a great experience in this topic, acquired during his participation in the Finnish government activities, including that which were regarding COVID-19 response. So it will be a lot of interest for all of us to watch his talk on these affairs. Please, Ahti.
Thank you very much for the introduction. And I have entitled my brief presentation as Producing and Using Model-Assisted Policy Advice, and actually I will be emphasizing the using aspect, given that the previous speakers have wonderfully addressed some of the topics in producing. And my roles in Finland include some responsibilities in the government foresight group, where we have some 12 experts to guide the government in assessing national foresight work, to catalyze new activities and to comment on previously commented one. And in relation to COVID-19, one of the challenging appointments which I did have as a member of the COVID-19 science panel was to support the so-called working group consisting of the chiefs of staff from the different ministries to prepare a plan for the Finnish exits strategy. And this was already in April 2020, May 2020. And for instance, we were asked to provide inputs to the decision whether or not schools should be reopened at that time. And also further to the notion that we are talking about producing research, but in any given country, there's only so much research that can be produced. But we can also look at the question, can we perhaps facilitate the transfer of research from other countries? And in Finland, since last August, we've had a process so-called COVID-19 study review, where we have some 12 researchers, appointed researchers, producing summaries, and my responsibilities would be in the areas of resilience and anticipation. And all of this is publicly available, and it's being communicated to some 1,700 participants, and it's in Finnish, but this is the Google translation. It's readable. So if you wish to take stock of the materials, please feel free to do so. Then some observations. I would say that there's been an unprecedented surge of advanced modeling activity, employing SIR, susceptible, infected, recovered models, soft computing, artificial intelligence, data science, whatever. And what is also notable that some of these studies have had immense policy impacts. The report by the Imperial College on the 16th of March 2020 was one of the key catalysts for the decision to introduce stricter policy measures in the United Kingdom, for instance. But it's good to note that actually some of the countries which have apparently strong or even the strong analytical capabilities have not been doing so well in the pandemic. And one key component in all of this is to realize that it is not only the policymakers who are decision makers. Each and every one of us is a decision maker in terms of our decisions. In terms of the decisions which we take. Can you please, there's someone else. Okay, and also when seeking to promote the transfer of research from other countries, it is good to remember that any given results need to be interpreted with care, because they've been developed for different contexts with their specific contingencies and peculiarities, and therefore they cannot be adopted as such. And now actually I would like to put on my hat as an educator in systems and operations research, and for purposes of excessive simplification, this is what I tell my students. These are the cornerstones of systems and operations research. We're looking at systems, typically complex ones. We seek to understand them better by building models with the aim of supporting decisions. And in this context, there are challenges for delivering model-assisted policy advice at this level, relating the system as such to modeling. We have, especially in the early phases, how does the virus spread? It wasn't really known. And at present, there are some new variants arising. So the very properties which they have in terms of their impact on health are not very well known. Then when we look at the interface between decisions and models, there are questions as to which one out of we can build so many models that actually there's a potential danger in that the decision makers will be confounded and confused as to which one, because the models may be telling different stories. And also the models may have different scope. And as a result, the implications beyond the intended scope or defined scope may also be of interest to the decision makers, yet they are not covered. And finally, we come to the interface between the actual decisions, policies, and the system. So do we really, can we be confident in expecting that people will obey restrictions? And how can we address trade-offs between different sectors of the economy or different regions? So all of this is quite complicated. And I would actually argue that there's a space for risk management, but the system, all this full range is so complex that there's a need for collaboration among the many stakeholders. And here I would actually point to one of the discussions which was quite influential in Finland. The president of Finland, Sauli Niinistö, he annually organizes these so-called Kultaranta discussions. And there was a process, and all of this was done online, virtually, using virtual tools. And the appraisal of the economic impacts in connection with those discussions was facilitated by a company called Inclus. And I'm pleased to know that actually that company has emerged from some of the complex and sensitive peace mediation processes which were facilitated by Crisis Management Initiative, established initially by the former president Martti Ahtisaari, also the Nobel Peace Prize laureate. And how did this company come to be? Actually, it sort of relates back to some of the research we did some 10 years ago at Aalto University, together with Villa Brummer, now the program director of CMI. And as a result, there's been a maturation of the methodologies from methodological research at the university via further enhancements at CMI. And actually, one of the questions which I would like to pose, in a sense, is that is it the case that actually crises are something which spur the development of new methodologies? And if I think of one of the most significant previous crises, so some 12, 13 years ago, we had the financial crisis. And therefore, there was a huge interest in seeking to understand how the financial sector is, what kinds of interdependencies are there. And one of the companies which, in a sense, also links back to our research here at Aalto University is that there's a company called FNA, which has been quite successful, as in evidenced by the numbers above. But again, that too links back to the work with which a former student of ours had first at the Bank of Finland and then at various central banks. And this is the, let's say, the migration path. And here my key point, in a sense, would be that as researchers, we are oftentimes incentivized to produce more and more of research. But actually, from the viewpoint of enabling the uptake of that research across the broad spectrum, it should be a landscape where we actually have some companies which then take some of these activities forward. And I was also very pleased with the comments by previous speakers that we do need improved methodologies, and this is also in the area. We had a paper in decision sciences, but developing methodologies. So I would say that they're an ever-pressing key need to produce advances in dynamic optimization, stochastic optimization, and so on. And finally, I would conclude with a few reflections. So I would say that there's an ever-present, if not ever-growing need for methodological advances. There are exciting frontiers at the interfaces between decision and policymakers, systems and models. And I would say that actually the elements by which the human component, people component, needs to be embedded. I've been very pleased to hear about the agent-based modeling approaches in linking to the model, so that actually the models, in a sense, will be shifted as if it were from the third place to the second one so that they actually do become the kind of a focal lens which really helps us understand systems better. And finally, 2 remarks I wish to stress: that the behavioral assumptions which we make in seeking to capture the essence of these complex systems, it also needs to be understood and accounted for in producing and using policy advice. It is oftentimes the hardest one to get a good hold of. It's about people, and people are sometimes unpredictable. And also I would argue that sometimes the development of these novel methodologies in practice, it may call for the iterative incremental changes in organizational practices, and therefore it may take time. It doesn't happen overnight, as exemplified by the 2 companies I mentioned previously. So thank you very much, and I look forward to our discussion.
Thank you, Ahti. Thank you for presenting us that achieving a compliance between models treated by system analysts and real policy making is not so simple. And that we must keep in mind. And you're right saying it is very iterative process, especially in such hard conditions as we had during COVID-19 pandemic. And I agree with you that some countries having outstanding analytic capabilities in all senses of these words dealt very hard with this pandemic. As we have learned from the bright talks of our panel speakers, there exists an evident optimism in the assessment of future efficiency of systems analysis as mathematics of the 21st century, and as it is often referred. I do share this optimism and should be so ambitious to affirm that future achievements of systems analysis in complex problem solving will depend on its convergence with 2 intensively developed areas, big data and artificial intelligence. Big data, in fact, is a new way of thinking of large-scale systems operation, and those who would be able to implant the big data tools and technologies to systems analysis toolkits and frameworks would be able to develop and apply much more close to reality and adequate models of real systems and problems. From the other side, implanting to the aforementioned frameworks tools originating from the artificial intelligence and machine learning, especially that of the knowledge engineering area, provides much more rapid and flexible modeling. That is very, very actual, as I said, when we need to have many iterations to achieve the most adequate model. We have saw it just now from the Dr. Rovenskaya talk and Professor Salo talk, where such tools made agent-based and origination from the multi-agent systems area as one of the advanced AI technologies were successfully applied. And also application of the AI-based approaches would simplify an interaction between systems analysts and decision makers, providing easy and rapid creation and maintenance of knowledge bases reflecting system structure and logical operation. So I think that our panel discussion was very useful for all of us, broadening our perception of systems analysis and its frontiers. Let me thank all panel speakers, Fred, Abraham, Ahti, and Elena for their brilliant talks, and for time they have spent preparing their talks and participating in our panel. Thanks to all who have watched the panel via Zoom and YouTube. And thanks a lot to the IIASA staff, especially to IIASA Director General Albert van Jaarsveld, for organizing this remarkable event. Wish you all to be healthy and wealthy. Please save yourselves in these hard times. Good luck.